Hey pre-AP students, we're going to go over some Lewis dot structures today, which sounds very similar to Lewis dot diagrams, and you'll see here in a second why that is. A little bit of background about these. They are working with covalent compounds. Remember, covalent compounds are nonmetal plus nonmetal, and those are both anions. So they're both trying to get electrons. They don't give them up. They're trying to get them. So they form covalent bonds which share electrons. And what we're going to be looking at is the way that those electrons are shared. A Lewis dot structure is going to basically be a diagram that shows where electrons are shared, where electrons are not shared, and it's going to dictate the shape of the molecule, which we'll look at tomorrow. And when we're drawing these, we basically are going to call them skeletons, showing where all of the bonds are, where the electrons are shared, where the electrons are left as lone pairs. For an example, I'm going to draw you a carbon tetrachloride molecule. That's one carbon with 4 chlorines. So this is what this molecule would look like. You've got 1 chlorine in the middle that is bonded to 4 different chlorine atoms. Now what you need to see here is that the electrons are surrounding the atoms, but they are also in these bonds. These bonds are formed when electrons are shared. And in each bond, there are 2 electrons. So let's look at this bond. I'm going to zoom in on it, okay? So we've got this bond right here on the right-hand side. Carbon starts off with 4 valence electrons. It donates, or kind of sticks out there, it's one little electron to be in this bond, and chlorine also sends one, because chlorine initially had 7. 1, 2, 3, 4, 5, 6, 7. So carbon puts 1 in the middle, chlorine puts 1 in the middle, and they share to form a bond. So a one-line bond like that is 2 electrons that are hanging out there. We just draw the line to say they're bonded. And that's true for each of these lines. Here we've got a carbon valence electron and a chlorine valence electron. Same with chlorine and carbon over here on the left. All of these bonds are 2 electrons. Now, if you go count up the number of valence electrons for each of these atoms, you'll see that the octet rule is fulfilled and they have 8 according to the sharing. So carbon here in the middle has 1, 2, 3, 4, 5, 6, 7, 8, which is because chlorine is sharing with it in all of these different places. Originally, it only had 4. And if you look at each chlorine atom, it starts off with 1, 2, 3, 4, 5, 6, 7, and then it gets another one shared by carbon. You can count them up for all the rest of the things. So each atom here has 8 electrons in its valence shell, and those are being shared between carbon and chlorine as represented by those bonds. So what we're going to figure out for the rest of the lecture today is how to draw these things from scratch. Now there's a whole list of steps right here. You're welcome to read through them. I'm going to go through them step by step with this example, CH4, rather than just reading them off to you. So let's look at CH4 down here in this empty space. The first step in finding the Lewis structure is to calculate the total number of valence electrons held by all of the atoms. And we're going to use the atoms that are in our formula to figure that out. The first thing you do to figure out the total number of valence electrons is write down each of the elements. We've got carbon and hydrogen. For each element, you write down how many atoms are in the compound. Carbon has 1 because it doesn't have a subscript. Hydrogen has 4 because it's got a subscript of 4. Then you figure out the number of valence electrons for each of these things. You do that by looking at its group in the periodic table. Hopefully you know how to do that. If you don't, Google it, ask a teacher, figure it out somehow. Carbon has 4 valence electrons, and hydrogen has 1 valence electron. So what you do is you take these numbers and multiply them. Carbon has 1 atom times 4 electrons, 4 valence electrons in that atom. Gets you 4 valence electrons total from carbon. Hydrogen has 4 valence times 1 valence each for a total of 4 valence electrons. So overall, in the whole compound, you've got 8 valence electrons available for sharing and bonding. Now, something you're going to see as we progress through this is that we don't care so much about that number as the number of pairs. So we're going to take that number, divide it by 2 to figure out the number of pairs. 8 electrons divided by 2 becomes 4 electron pairs. So we've got 4 pairs to spread out between all of the atoms. Now we move to step number 2. Take the element with a single atom and write its symbol down. That element here is carbon. That element's going to go in the middle. And we place 4 bonds around it. 1 bond, 2 bond, 3 bonds, 4 bonds. And remember that each of these bonds is really just 2 electrons hanging out. There's like 2 electrons inside each of those bonds. So we've put the 4 bonds around. Next thing is place the other elements around the center, 1 per bond. So we'll do hydrogen, 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 hydrogen. And there are 4 hydrogens, so that works out. Step number 4, change leftover bonds into lone pairs on the center atom. There aren't any leftover bonds here. All the bonds got used, so we skip that step. Number 5. Fulfill the octet rule for each of the outer atoms by giving it 3 more pairs. The bond counts as one of its pairs to make a total of 4 or 8 electrons. However, this step does not apply to hydrogen because hydrogen only needs 2 valence electrons to be full. And if you look at each of the hydrogen atoms here, it's already got its 2 valence electrons in the bond. Each of these hydrogens has 2 valence electrons from the bond. 1 that it donated to the bond, and 1 that carbon donated to the bond. So those are all good. All of the hydrogens are satisfied. Carbon has 8 valence electrons shared there in the bonds, so it's satisfied. We move on to step number 6. Count the number of electron pairs and the number of bonds. So I'm going to go ahead and do that. I'm going to do that in blue. Count the number of electron pairs. Are there any more electron pairs? Nope, there aren't any hanging out around atoms. They would look like this if they were. They would look like 2 little dots. But we don't have any of those. So we're going to go count up the bonds. We've got 1, 2, 3, 4 bonds. If that number is equal to the total number of pairs that we found in our math, we're done. So we got 4 pairs and 4 pairs. All of the electrons are counted for. We don't need any more electrons. Everything is good. So we're all done, and that is the Lewis dot structure for CH4, which I believe is actually called methane. Now, I know that was super quick, and that was only one example, so we're going to do another one together. It's a little bit more difficult. It is carbon dioxide, CO2. So first and foremost, you have to do your math to figure out the number of electron pairs available for you to work with. So we do that starting with the 2 elements, carbon and oxygen. There is only 1 carbon in that compound, and there are 2 oxygens. Multiply that by their numbers of valence electrons. Carbon has 4 valence electrons per atom, and oxygen has 6 valence electrons per atom. So you multiply those to get the products, and then add those to get the total number of valence electrons. 1 times 4 is 4. 2 times 6 is 12. That gets you a total of 16 electrons. And then you make that into electron pairs by dividing by 2. 16 electrons turns into 8 electron pairs. And that's your math. You know, you have 8 electron pairs that you can use to share inside your molecule. Step number 2, write down the singular element in the middle. So I'm going to write carbon right there. Then you make 4 bonds. 1, 2, 3, 4 bonds for carbon. And we'll put the other elements around bonded to carbon. Now there's only 2 oxygens. So after you write your 2 oxygens, you have 2 bonds left over. And we know that each bond housed 2 electrons in it, like this. You don't have to draw these every time, I'm just drawing them for teaching purposes. Now some of these are actually used in a bond, the ones that are connected to oxygen. Those that are not actually used in a bond stop being a bond, they stop looking like a bond, and those 2 electrons become pairs on this center atom. So I'm going to draw them there and erase the bonds. But still it's the same number of electrons. Now carbon is fine. Carbon is happy. It's got 8 electrons between its pairs and its bonds. But the oxygens are not happy. They only have 2 electrons right now. They need to fill up their octet. We fill up the octet just like this, putting pairs around the oxygens. Now everybody is happy. Oxygen has 8, carbon has 8, and oxygen on the right-hand side has 8. Everybody's good. Now we have to count up all the electron pairs and make sure it's the same number as we had available, because if there's more electrons here than we had available, there's going to be a problem. So we count up all of the electron pairs. We've got 1, 2, 3, 4, because those in the bond still count, 5, 6, 7, 8, 9, 10. That is 10 pairs of electrons right now. But our math earlier dictated that we could only have 8 pairs. So we've got to figure out how to consolidate these electrons and get rid of some of these pairs and have everything still be fulfilled by the octet rule. And in order to do that, we're going to erase some pairs off of these outer atoms and off the inner atoms and share them. So instead of having 2 electrons here on oxygen and 2 electrons here with carbon, they're going to create another bond that holds 2 electrons that will share. So now oxygen still has 8, carbon still has 8, but there are 2 bonds there and less pairs that are unshared. Now let's count up all of the pairs of electrons again. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9 pairs. So we are closer than we previously were. So this time we're going to take away some electrons from this other oxygen atom and the other pair of electrons from carbon and have them share in the middle again. So we're going to create another bond there that has 2 electrons in it and count up the pairs yet again. 1, 2, 3, 4, 5, 6, 7, 8 pairs, which is the correct number that we should end up with according to our math at the beginning. So this is going to be carbon and oxygen bonded together with double bonds. Okay, so there will be 2 bonds, each consisting of 2 electrons between carbon and each of the oxygen atoms. Note that there is a rule here that says before you create a triple bond with an atom, every bond has to be double. So basically what that means is when we were drawing this and we had to create a double bond with this left oxygen atom, we couldn't create a triple bond there and leave this one over here as single. We had to make a double bond with each element. So this one down here is correct. This one on top is not. Now let's look at one final example. It's going to add a tiny layer of complexity. And that is because this is a polyatomic ion, which means it has gained some electrons. But we'll deal with that in a second. To start off with, we use the same process we've been doing. We write down the elements, sulfur and oxygen. Sulfur just has one atom in the formula, and oxygen has 4, which you can tell from its subscript. Each of these has a certain number of valence electrons that you can find according to its group on the periodic table. Sulfur has 6 valence electrons per atom. So you take the one atom, multiply by 6 to get 6 total valence electrons for sulfur. And then for oxygen, you multiply the 4 atoms by 6 because each oxygen atom has 6 valence electrons for a total of 24. Add up those two, you get the whole compound has a total of 30 valence electrons. But because this is a polyatomic ion, it's got this -2 charge. That -2 means it's going to gain 2 electrons. So we have to add 2 to our total to get 32 valence electrons. Divide that by 2 to get pairs. 32 divided by 2 is 16. So we're going to have 16 electron pairs to work with to build our Lewis structure. Step number 2, after you do the math, is writing down the single atom in the middle. Single atom here is sulfur. Just write down sulfur in the middle of the diagram and give it 4 bonds. On each bond, you put one of the other elements. We've got 4 oxygens, so they go all the way around. No bonds left over. And we know that each of these bonds is going to contain 2 electrons. So now we have to fulfill the octet rule for each element. Sulfur is all good because it's got these 8 electrons in the bonds. We've got to add all of the electrons for oxygen. That's going to be 3 pairs or 6 total electrons per oxygen atom, like so. And now we count up all of the pairs to see if it matches up with our 16 calculated pairs. Starting here at the top, I'm going to go ahead and count. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 pairs, which matches exactly our number of calculated pairs. So everything is fine. This is the Lewis structure. But because it's a polyatomic ion, we have to do one tiny little extra step. And I'm going to redraw this really quickly so that you can see it. We've got sulfur with the 4 oxygens and 6 pairs around each oxygen. So without all the highlighting, that would be the Lewis structure. When it's a polyatomic ion with a charge like that, the last step you have to do is put it in brackets like this, and then put that charge on the outside. So this one is going to be the polyatomic ion SO4 with a -2 charge.